Okay, this week we're going to kind of continue with our earthwork discussion and look at shrink and swell factors and then also mass diagrams. And this is the point in at least this course where I hope you start to see that a lot of this material from other courses in the curriculum start to kind of come together and the big picture starts to develop in front of you. You're definitely going to see an influence from the soils class uh, in the first year, also the surveying materials that we've been going over, and depending on where you're at in civil drafting, all of these courses kind of come together when we talk about this subject in particular. And when we're talking about soil, has three different expressions or conditions that we find it in. A bank condition, a loose, and a compacted condition. And up here in the upper diagram, you can see a bank condition is soil when it's in its natural state, before it's been excavated out and not when it's been compacted into a site. So this is just kind of in situ soil. If you've excavated that material out because you need to move it, for a cut scenario on a construction project, you've changed its properties. You've increased the volume or the amount of airspace between soil particles, and we now call it loose. It's loose material. And the same mass of soil now takes up a larger volume of soil, and that's going to be expressed here as a swell here in the next slide. And then we're going to take that loose material, right? We're going to load it into a truck. We're going to haul it away somewhere else and hopefully use it on the job site. And then we're going to compact it. And the process of compacting, if you remember back to soils class, actually decreases, right, the amount of void space between soil particles. So now that same mass of material, whatever it weighed in pounds, takes up less space than it originally did when it was in situ. So now we call that a compacted cubic yard, or a compacted material. And that relationship is expressed as a shrinkage percentage. So we have these three different expressions of soil, um, and we're going to put things in terms of a cubic yard, because that's how earthwork, right, is quantified. We have a bank cubic yard. It's going to swell up to a loose cubic yard, and then it's going to shrink down to a compacted cubic yard. And depending on where you are in your company's operation, depends on what you're concerned about, right? If you're on the application side in the field, you care about bank yards and compacted yards, right? How much material are you going to dig out of one side hill, and how much space over here do you need to fill in a fill scenario, right? If you're an estimator working in the office and you're worried about number of cycle times with loading trucks, the time it takes a loading truck to fill up, drive, and then deposit, right? You're probably caring more about loose yards. So you can use any one of these units for an application on a construction site, but whatever you do, you want to make sure you reduce all of these scenarios into equivalent cubic yards, right? You don't want to compare apples and oranges here. Put everything into bank yards, or put everything into compacted yards, or everything into loose yards. That's probably the least common, and it's not what we're going to talk about in this class. So just a quick discussion on how some of these variables are calculated. Right, your swell percentage is simply the soil's bank density divided by its loose density minus 1, and then times 100 to put it in terms of a percentage. And the shrinkage percentage is kind of the reverse. It's 1 minus the bank density over your compacted density times 100 to put it in terms of a percentage. And I'm putting density over here in an example in terms of units that we're a little more familiar with from the soils class, right? Pounds per cubic foot. Um, if you remember when we did the Proctor test and the sand cone test towards the end of last spring, we computed what was the maximum potential density a soil could achieve, right? We did that through the Proctor test, and then we went out and measured it in the ground. And that was kind of an in situ, or maybe a compacted, if that soil has been compacted intentionally, condition. And these are approximately the numbers you're going to deal with when you're dealing with compacted soil. Right, this is maybe on the low end, 114 pounds per cubic foot. And you could probably find some soils that are going to compact down into a density of 125, maybe even 130 pounds per cubic foot. Soil in its natural condition, we generally say its density is about 100 pounds per cubic foot. Might be a little more than that, depending on how moist it is. And then once it's dug out of the ground and put into a pile or loaded into a bucket, it's going to weigh quite a bit less because you've increased a lot more air into the volume unit. So if we wanted to compute the swell percentage and the shrinkage percentage for the soil, you're simply taking, for swell, the bank density divided by the loose density minus 1 times 100, and it would have a 15% swell. So what that means, I guess in real terms, is that the same amount of soil, right, that 100 pounds of soil that you dug out of 1 cubic foot of space in its bank condition is now going to take up 15% more space. And that's very significant if you're trying to determine how many haul trucks you need on a job site to move material around. Shrinkage percentage is more important to us for this week and for this class. It's how much is it going to shrink when it's compacted. So in this case, it's 1 minus your bank density divided by your compacted density times 100, or a 12% shrinkage. So again, that 100 pounds of soil that we dug out of 1 cubic foot of space is now going to take up 12% less space when we've compacted it in a fill scenario somewhere on a job site. And that's why when we talked about balancing cuts and fills up there in Thompson Park, I kind of made that little qualifier, is that you don't want to balance equal cut volume with equal fill volume because the soil's not equal, right? It's an apple and an orange. So you need quite a bit more cut on a job site to occupy the same a volume of fill on that same job site. And that's all dependent on how much shrinkage is going to occur when that soil is compacted. So to compute those numbers, we look at things called a load factor and a shrinkage factor. And we're really not going to deal with load factor. That's more about quantifying the expansion of soil when it's going into coming out of the bank and going into a truck. But it's simply the loose density divided by bank density. Or, because we've already kind of computed your swell percentage, your load factor could be expressed as 1 divided by 1 plus your swell. Swell being your swell percentage, but expressed in decimal terms, no longer percentage terms, right? So take 100 out of that. What we're going to care about is shrinkage factor, right? And your bank volume, which is how it is coming out of the ground, can be multiplied by a shrinkage factor to obtain the compacted volume, right? So once we dig soil out of the ground and go move it, how much space is it going to occupy once we compact it down? And that's equal to your bank density over your compact density, or it could simply be reduced as 1 minus your shrinkage, where this is your shrinkage percentage, expressed in terms of a decimal again. So I don't like the fact that shrinkage uses the same word for two different meanings. Back on the previous slide, right, we used shrinkage to define a percentage, and now we're also using shrinkage to apply it to a factor used in another calculation. But this shrinkage factor becomes important for us here when we look at this mass diagram next, and we need to convert all soil volumes into equivalent bank cubic yards, right? We want to deal with apples and apples. So this was a table that comes out of some of the reading chapters I'm putting on Moodle for you this week, since our book doesn't really get into this kind of earthwork. I have some other documents posted for you. This is just a nice summary table of typical soils you find on a job site: clay, common earth, rock, and gravels, and then the approximate swell and shrink percentages that you could expect these soils to be, and then also the approximate load and shrinkage factors that would be used for these soils. And these unit weights are in more of a construction units, pounds per cubic yard, not the pounds per cubic foot that I've been talking about. But remember, I said common ground in its natural state is approximately 100 pounds per cubic foot. Well, here they're saying it's about 3,100 pounds per cubic yard. Right? So if you take this divided by 27, that'll reduce it into pounds per cubic foot units. So they're saying it's approximately 114. That's a little heavier than I've heard as far as estimates on common ground. What's interesting about this table is to see that you can have a negative shrinkage factor, right? And that's the case with rock, right? If you've got bedrock and you've got to blast it out of the ground, when you go and move that blasted bedrock to another place on your job site and place it to use as fill material, you're never going to get it to occupy less space than it did when it was bedrock, when it was unblasted. So a rock is the one case where it's always going to swell up, regardless of if it's going from bank to loose or bank to compacted. It's always going to get bigger. Okay, so here's where we're going to kind of rehash a little bit about what we did last week, so we can kind of set the stage for how we interpret a mass diagram. And then I want you to look at this top left picture first. This is a typical profile drawing. So this is a drawing that represents natural ground, which is this curved line up here, and a design surface, or design ground, which is represented by the straight line. So apparently this project is going to take some rolling hills and flatten it out into a flat roadway that's climbing at, looks like, a couple percentage grade. And this roadway is identified by stationing, right? So here they're showing every 2 stations, and at each of those stations, right, you can take a slice through the earth, just like we did last week, and create a cross section. And that's what we see down here in the bottom left-hand picture, are example cross sections for various portions along this job. Right, your cross section could be like showing up here, all cut. It could be a bigger all cut section, or it could be a mix of cuts and fills, like it's showing down here in the bottom. And depending on what your cross section is doing, right, you can calculate the cross-sectional area. And if you have cross-sectional areas between succeeding stations, right, you can start to quantify the volume of material or earthwork between stations. And like we looked at last week, average end area method is the easiest and probably the most common way to do that. So once you're reduced, your survey including the slope staking, right? Here's our catch points. And we've taken those catch points and we've computed cross-sectional areas and gotten earthwork quantities. We can come over and develop a table like showing here to the right. And this table is simply listing your stations from beginning of project, right, to end of project, and the earthwork that's occurring between those stations. So you can see in our profile drawing here, from the beginning at 0 plus 0, 0, all the way up here to approximately station 15 plus a pair, it's all cut. So in our table here, that's all we have. We're showing cut volumes expressed in bank cubic yards all the way up here to station 15 plus a pair. We have no fill, right? We don't incur a fill scenario until we proceed beyond station 15 plus a pair. And then we're all fill all the way up until 36 plus a pair. So that's what you see in the table here. And these numbers represent the individual earthwork between those succeeding stations, right? We stay in fill until 35 plus 50, or about 36 plus a pair. We go back to a cut scenario, and then we end the project with a fill scenario. And I'm going to skip this third column, or the fourth column here for a second, and I want to look at this last column here, the mass diagram. These are the data points that we're going to be plotting here on a mass diagram in a second. But you'll notice here, these are an accumulation running total here. At the beginning of the project, obviously we have 0 earthwork. At station 2 plus a pair, we've accounted for 22,500 cubic yards of cut. So our accumulated total is 22,500 cubic yards of cut. Right? At station 4 plus a pair, we've gained another 76,000 cubic yards of cut. So now we've accumulated an additional 76,000. So we're up to almost 100,000 cubic yards of cut. So you can see this is a running total, right? It's accumulating on itself. And then once we get into fill scenarios, right, we attained a total of 833,000 cubic yards of cut up to station 15 plus a pair. And then we start going into a fill scenario. And once we're filling, right, we're going to fill 18,000 cubic yards. You can see our total went down. So that's why these last couple weeks I've talked with a few of you individually about how we typically call cuts positive values on an earthwork project and fills are negative values. And it's because when you cut something on a job site, right up here, once you start cutting into natural ground, you have that earthwork to spend somewhere else. It's like a bank account, right? If you're making deposits into your bank account, you can go spend that money somewhere else when you have a debt. Well, when we cut earth out of the ground, we've got a positive earth account. We can go spend somewhere else, and we spend it where we're in debt. And we're in debt in a fill scenario, right, where we have a big void that we need to fill up. So it's kind of counterintuitive, calling a cut a positive number and a fill a negative number, but that's how these numbers are generated. This accumulated total is accumulated. We're going to be decreasing now every station as we proceed along the project in a fill scenario. And here we're even going into negative values, right? We have more fill needs than we have soil available from our cuts. So up to here at station 35 plus 50, we're almost 500,000 cubic yards deficient. Good thing we start to get into another cut scenario on that job site. So we're back into our positive portion of the balance sheet, and that 500,000 starts to get closer to 0, so we're going to be increasing, and there at 46 plus a pair, we're back into the positive. So we do have enough cut all along that job site at least up until this point, to balance out for us. And we have this cut scenario. We end with a fill. So down here, we're back into our negative values, and we're going to be decreasing. So at the very end of our project, you can see we fell short. We fell short 200,000 cubic yards. So that's the amount of material that would need to be purchased or imported, either from a nearby gravel pit, or maybe you can even establish a gravel pit on site. But now I want to look at this fourth column here, this equivalent bank cubic yards. And you can see it's only applied to your fills. And I have this little equation down here. Equivalent bank cubic yards is equal to a bank cubic yard times 1 over your shrinkage factor. And what we're trying to do here is express how many bank cubic yards of material it will take to occupy this many cubic yards of fill space, because we know earthwork is going to get smaller when we compact it. So in this cut section of our project here, we need to cut 21,800 cubic yards of material, because when we haul it over to a fill and we compact it, it's only going to occupy 18,200 cubic yards of space. And when you're running your accumulation of values, right, you want to be adding and subtracting apples and apples. So cut is already in bank cubic yards because we're cutting it out of the natural ground condition. But fill needs to be converted to an equivalent bank cubic yard based on that shrinkage factor. And if we do that, that number is always going to get bigger, unless we're dealing with pure rock, right? Because we looked at that last table. But we're going to need more cut to occupy the same space of fill due to shrinkage factor. And if we convert that, now we can just add and subtract as we go along here, because we've got apples and apples. So this is a mass diagram, and once we have that table of values computed, we can plot it on a mass ordinate. And I've put that in purple down here, and it helps to visualize a mass diagram when it's corresponded to its equivalent profile diagram. So up here on top, this is the profile diagram that we just saw. Right, here's your natural ground going up and down, and the design grade, so you know where you're cutting and where you're filling. And your mass ordinate that is developed for your mass diagram by placing 0, which means your 0 cubic yard balance, right? And that's just a horizontal line. And then you have positive bank cubic yards above that ordinate and negative bank cubic yards below that ordinate. And even though this looks like a profile drawing, don't let this shape confuse you into thinking that this represents a hill and that this portion represents a valley. These are simply a visual representation of the numbers that we came up with over here. And that's the biggest thing that confuses people when they start to look at mass diagrams, is they want to interpret this line as an actual surface of some kind, but it's not. It's just a balance sheet. So what it represents is the amount of material you have available in your bank account, or your earth account, if you want to call it that. And if you come up here and think about your actual ground surface, your profile, you can see, remember, right from 0 plus 0 all the way up to 15 plus a pair, we were cutting. And that means every time we cut, we're making a deposit into our bank account. So on our mass diagram, we're plotting positive data points. And from 0 to station 2 plus a pair, let me go back one more time, we accumulated 22,500 cubic yards of material. So at station 2 plus a pair, you come up positive 22,000 cubic yards on your ordinate. And then at station 4 plus a pair, right, we accumulated 99, we were up to 99,000 cubic yards of material. So here at station 4 plus a pair, we're going to plot positive 99,000. So this is really just a series of data points that we can connect and smooth into a line to make it look nicer. But we're continuing to cut all the way up to station 15 plus a pair. So our balance is going to continue to increase all the way up to station 15 plus a pair. Once we've entered into a fill scenario in our profile, right, now we're starting to spend that earth, right, just like you're spending your savings out of the bank. And if we're spending our savings, our balance in our earth account is going to go down. And if we look back again at our balance sheet here, we were positive, increasing up to station 15. We're positive, but we're decreasing, and we keep decreasing until right here around station 27 plus a pair. That's where we go from positive to negative. So we know we passed a threshold, and we ran out of earth, because we went all the way to 0 and then negative a little bit. And that's what's represented every time your mass diagram crosses your mass ordinate. When you go back to 0, right, come over here, that represents 0 earth available in your earthwork account. And if we look back up at our profile, because we're still in this fill scenario, right, we're going to be filling until we get up to station about 36. You're still spending money. You're still spending earth. So you've decreased and now you're negative. But once you've gotten to another cut scenario now we're starting to gain money. We're putting money back into our account. So we've reached our minimum, and now we're increasing our bank account back up. And boom, we hit a balance again. We're back at 0 there at station 47 plus a pair. So that's a good thing. Whenever you can hold your mass diagram close to 0 at the end of your project, it means you've done a good job balancing your cuts and your fills, and you're not going to have to spend a lot of money hauling material away, nor are you going to have to spend a lot of money bringing import material in. So you can always see just visually, if you've plotted your mass diagram, if you've ended below your ordinate, you have a net deficiency, and this is how many cubic yards of material need to be brought in. We can start to use this diagram then to lay out kind of an estimating schedule and plan of attack. So we know every time we've crossed our ordinate line, our 0 line, with our mass diagram, we've balanced our earthwork account. So if we drew lines from our 0 points straight up into our profile, and we do that every single time. So we got another one over here, and we have a third one over here. We know up here in profile view, that's where in the real world on our project our earthwork balance is. And we can start to develop a plan on how we're going to move this earthwork around, right? Which cut stations are going to go to which fill stations. And it's pretty easy to visualize. We're going to need to take this cut and move it over into this fill. And we're going to run out of that cut material by the time we get up here to station 27 plus a pair. So we got to go somewhere else to go get some earthwork. And we're going to use this cut and bring over to this fill. We've balanced to 0 at this red line. So that means we have these two little sections that are going to balance for one another, and we can move that cut over into that fill. And because we were 200,000 cubic yards deficient at the end of our project, this is the location on the project where we're going to have to bring in our import material. And the other thing that you can do here on this mass diagram is develop a rough approximation on how far your trucks, your haul trucks, are going to have to be driving to move all this material around. So if you look at each individual section um, from balance points, right, 0 point here to 0 point here, you have a peak, and you can draw a vertical line from the peak down to your ordinate, and then halfway along that vertical line, you can draw from the left edge of your mass diagram to the right edge of your mass diagram. And because your horizontal scale is represented in stationing, right, that's just a horizontal distance. The length of that line represents the average haul distance that the trucks are going to have to make to move this cut section over into this fill section. And you could do the exact same thing then over to your next balance point. I didn't do it on this diagram here, but you could draw a vertical line right there. Halfway along that vertical line, you draw a horizontal line, and the length of that horizontal line represents the average haul distance it would take trucks to drive to move this material over to there. And that's where this becomes a very valuable tool for an estimator, because if you know the loose yard volume of material that's going to come out of that cut section, and you know how you then know how many truck trips it's going to take to drive, and if you know the average haul distance each truck trip has to take, you can start to determine your fuel costs, your time costs, and then your labor costs. Maybe how many trucks do you want? 8 trucks running 2 cycles an hour, or do you want to have fewer trucks running more times, right? It's all about trying to minimize the amount of time each piece of equipment runs idle on a job site, right? If you only have one excavator cutting, you probably don't want 8 trucks sitting there waiting to be filled up, because your trucks are going to be waiting while one excavator works. Similarly, you don't want to have 8 excavators with only 4 trucks. So this is another example from a different document that I'm putting up on Moodle for you this week. It's kind of the same thing here. You've got your profile view above, so this is the actual ground surface. And your design surface is then just a plain old flat road, so maybe we're building a road in Iowa or Kansas. And you can see you're going from fill scenarios to cut scenario to fill to cut to fill. And we don't have numbers attributed to these earthwork stations here, but you can kind of see how a mass diagram would develop, right? In this fill scenario, you're spending earthwork before you even accumulated any, so you're going to continue to lose earthwork in your account. And typically, these peaks on your mass diagram, right, peak deficiency of earth or peak accumulation of earth, will coincide with your transition points in your profile, right? When you've accumulated, or when you've transitioned from fill to cut, will coincide vertically with your peak. And when you've transitioned back from cut to fill, it'll coincide with your peak. So I want you to spend just a minute or two, or longer, thinking about how you would project your balance lines from your diagram up to your profile and start to develop a plan of moving this material around, because the next slide is going to develop that here for you. So this is just that next slide, and you can see just like we showed in that last example, you come vertically up, and then you can start to see where your where your cuts are going into which fills. Cut into this fill. And down here they've also developed that haul distance using that kind of convenient approximation by going midway between your ordinate and your peak. This project shows a net deficiency at the end, which means we have more fill along our project than we do cut available, so we're going to have to be bringing in material.